So if you want the slides, I think you can go to the GitHub. I hope everyone sees my screen. If you can't see my screen, just unmute yourself and then remind me because I can't see anything. So this is basically the second times we organize a journal club. So the regular times that we organize is during Sunday night. I think 9:30 to 10:30. So for that session, I will be just going through Nelson and Chuang first. Today we have a slightly different schedule because some of the students that I talked to, they wanted to learn a little bit of error corrections, and just so that I need to go into stabilizer formalism, which is closely related to error correction as well. So that's why I have this special version of Journal Club, and be prepared to have quite a lot of exercise. Yeah. So the outline for today's Journal Club, basically we start with a very short introduction to classical error corrections. Then we go to group theory and stabilizer formalism. So over here, when we talk about stabilizer formalism, I will just very briefly touch upon a very simple quantum error corrections. Uh, all these are just introductory notes. I think if let's say someone is interested, then I will see how to arrange like a proper reading for each of these sessions. And then finally, I will just post my questions to Jianhao for the cluster states stuff. You guys don't need to work on the fourth session. So let's begin with classical error corrections. Usually when we talk about error corrections, let's say you have bits like zeros and ones. So the simplest way for you to protect your classical information is to repeat 3 times. So let's say you have the bit 0, so it becomes 000. So then you can apply your majority rule. If let's say one of the bits are getting flipped due to some errors, so let's say now it becomes 001. So because of the majority rule, basically you know that the correct bit is 0, so you can change the last bit back to 0, so it becomes 000 again. So this is a very basic concepts of how you perform error correction in a classical way. So over here, I will try to formalize a little bit what is classical error corrections. You see that later on. So basically, in classical error corrections, depending on what kind of error correction codes that you are running, so you try to encode some message of k bits, which is denoted by this particular vector m, into longer strings of bits called the code words. So over here you have what we call as the parity check bits, and they are also labeled as another vector p. So in this case, we have one bit of message, and then the other 2 bits are what we call as the parity check. So in a more general notion, basically your code word consists of 2 vectors being added up together, so to say. So the first part, starting from the first entry until the k entry, we call this the message vector or the message bits. and then the second half will be the parity check bits. Um, so we take note that for the parity check bits, they have to satisfy a set of equations of what we call as parity checks. So these parity checks, they are basically a vector, and the condition that we impose on the parity check um, vectors is such a way that uh, when you multiply with your code words, they basically gets you 0. So over here, you need to start paying attention the dimensionality of everything. Um, sorry. So if you look at if you collect all the parity check vectors together, you can sort of like form a matrix. So for the moment, we try to write in this particular manner equation 3. Because hi is a vector, so usually we denote vector as a column matrix. So if you want to fit into a matrix form, we try to do a transpose so that it fills up the row space of your parity check matrix. So then you can sort of like make equation 2 into a more compact form by writing out this matrix equation. So the parity check matrix multiplied with your code words, they are equal to 0. So this is basically how you would check your um, code words, whether or not some errors exist. So then the whole error correction codes is what we call as linear code. So what does it consist of? It consists of a parity check matrix H. Take note of this particular dimensionality so that you won't get lost with all the different matrices. So parity check matrix is n minus k multiplied with n matrix. So it means that you have n minus k parity check vectors, and then when you multiply with your code words, which is a n times 1 column matrix, then it gives you um, equals to 0. So that's basically what parity check matrix tries to do. So because your code words are separated into two parts, the first part is from 1 until k. The second part is from k plus 1 until n. So um, you will form a k-dimensional vector subspace, and this is coming from the message. And then you have another subspace later on, which is coming from the second half of your code words. So that will be, I think, n minus k dimensions. So this kind of code, we refer it to as the square bracket n comma k code. So n represents the total dimension of your linear codes. And then k will be representing like how many message that you are trying to encode. I hope this is fine. So this notation means that you are taking a set of integers. So if you just see the math BB Z2, this means 0 or 1. So when you see the n on top, it means that you sort of like repeat this n times. So that's roughly what are all the notations are being laid out in the first 2 slides. So the k-dimensional subspace, because it is by itself coming from your message vector. So you can basically try to find a set of linearly independent bases. So for that, we denote this as the bj. So this will be your basis sets. And then mj will be coming from your message bits. So again, we try to simplify all the notations without writing the summation sign. So you can also introduce another matrix called the generator matrix in such a way that your generator matrix is a n multiplied with k dimensional matrix, whereby it is given by all your bases up to pk. If you have this particular generator matrix, then coming from equation 4, you can see that your code words is basically equals to the generator matrix multiplied with your message vector. And then because we have the parity check matrix multiplied with the code words equals to 0, so you can sort of like plug in this particular part into that equation to become hash multiplied by g and then multiply with the message bits, they are equals to 0. But because we know that, of course, the message that we try to encode, they can't be 0. So it means that hash multiplied with g has to be equals to 0. So here, you can obviously see why the matrix hash is being defined that way, because your parity check row space, when you multiply together, you find that basically they are orthogonal to each other. So it basically means that all your parity check vectors, they are orthogonal to your basis sets for the message. So that's why your matrix hash is defined in this way as equation 6. By the way, if you have any questions, you can voice out as well. I understand the first few slides are very heavy because I need to introduce a lot of notations. So yeah, we come into examples now. So now here is what I said. Equation 6 basically the column space, or you can call it a row space of H, because I perform a transposition, so it becomes a column space. So you can also say that the row space of H, your parity check matrix, is orthogonal to the column space of G. So it means that your column space of H transpose is another vector space, which is what we call as the orthogonal uh, vector subspace of your linear code just now. They are also called the dual codes. So at this point, you might be wondering like, what is the significance of all this? So imagine that you have a set of equations like a1 vector v1, a2 v2, and so on. So sorry, I need to add 1 1 1 2 until 1n, and then you have a 2 until n minus k, 1 v1. So in linear algebra, when you have this kind of equations, usually the first equation, it means that your vectors are linearly dependent to each other. And then you have, let's say, n minus k equations. You would say that the linear dependence is of n minus k. So you can think of it in another way by writing down all your vector elements, um, v1 until vn. So all your vector elements is over the left hand side, and then you have a set of metrics over here. So this is basically coming from all the A's. So you can view this as your object, which is what we are doing. You can also see this as your dual side of your vectors. So later on, when you look into the quantum part, you can also see that we are also making use of this part of structures, whereby you have the main objects, which we call as the um, so in this case is the vector, and then the dual part will be something like the matrix. So later on you will see what I try to say over here. So let's try to do one example. So if let's say you are given a 6-tree code, the parity check matrix is H. So try to find the generator matrix G and the code words C. Sorry, uh, should be here. So you are given the parity check matrix and you want to find the generator matrix and the code words. So the easier part is to look at the code words first, because once you have the code words, your generator matrix is basically just the the set of your basis coming from your code words. So recall that just now we say that the parity check matrix multiplied with your code words equals to 0. So what will be the possibilities of your code words in this case? The first one is obviously all 0, because when h multiply with all 0, obviously it becomes a 0 vector, right? So what will be the other code words? Another one is 100 110. So now you try to multiply these together. Um, first one, obviously you get 1 plus 1, which is 0, because we are taking either 0 or 1. So the second one would be 1 plus 1 again, which is 0. So the third one is directly 0. So this is another code words. So try to find the other 6. You have total of 8. Try to find all the possibilities. When you multiply with h, your product is 0. you should have 1, 1, 1, 0, 0, 0, and then 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 1. The last one should be 0, 1, 1, 1, 1, 0. So all these code words, you have total of 8. When you multiply with hash, they should be equal to 0. So those are your code words. For your generator matrix, what you need to do is to select 3 vectors and excluding this one because this is just a 0 vector. So it gives you nothing. So you just select 3 of these code words and then formulate them into a generator matrix. So the ones that I have is this. So H is n minus k multiplied by n matrix. So your n is 6, your k is 3, so it's 3 times 6 matrix. This is your H. And then your G is n multiplied with n minus k matrix, which is 6 times 3 matrix. Okay. So this gives you like the matrix equations that are formulated above. It will help you to check how the metrics are being multiplied together. So your code words will be 6 times 1 column matrix. So that should be all your answer. So the next thing is about the Hamming distance. The Hamming distance basically is, let's say you are given 2 vectors, x and y. You are just trying to compare where are the differences. So that will be your Hamming distance definitions. By itself, it is a metric function, meaning that it is a sort of like distance function because it satisfies the 3 conditions for a metric function. The first one is that if your distance is equal to 0, then your 2 vectors are the same. When you switch around your vectors, x and y, the distance that it gives you is the same. And then it satisfies the triangle inequality. So whenever you have a function that satisfies these 3 equations, they are a distant function. So in this case, the Hamming distance for these 2 given vectors, you just look at where will be the difference. So it's 1, 2, and then 3. So the Hamming distance of the given vectors would be 3. The reason why we need the Hamming distance is because we need to know what is the minimum distance between your code words, which is denoted by a small letter d. So in this case, your code words C and C prime, you cannot take the 0 vector that I defined just now, even though they are part of the code words. But this is sort of like a trivial vector. So you can't take the 0 vectors as one of your comparisons. You try to compute So just now you are given 8 code words coming from this particular example. So you try to look at the 7 code words over here and try to find the minimum Hamming distance between your code words. So um, let's try to do now. So if you compare between these two, the first one is different, second one is the same, the third one is different, the fourth one is different, and then the others, oh, this one is also different. So this is 4. How about this? This is also 4. So if you compare these two, the first two are different, the third one is different, but the rest of the three are the same. So by comparing between all the 7 code words that you have 4 over here, 4 over here, and then you compare over here, you have 3. So by right, for this particular linear codes, your minimal distance D should be given by 3. So this minimal distance is important because they give you how many bits of errors that you can try to correct. So when you see this particular symbols, this is what we call as a floor function. So you try to compute the equation inside and then find the maximum integer that does not go beyond uh, this product. So in this case, your D is 3, 3 minus 1 divided by 2 is 1. So meaning that for the codes that we showed just now, you can correct a maximum of 1 error. So in that case, we try to write down the complete information for this particular linear code. So it will be a 631 code. The dimension of your linear code is 6. You have a 6 times 1 vector. You try to encode 3 bits of message into 6 bit of code words, and you can only correct 1 error. So this is a complete information for this particular linear code. So what the parity check matrix that we defined just now is trying to, so recall that your parity check matrix is 3 times 6 matrix. It tries to transform from the biggest vector space of your code words to the n minus k dimension of your code words. And the way to do it is just by multiplication. So if you have any transmitted information, coming from what you want to send, so this is defined by as the vector y. You multiply these two together. If they are not equal to 0, then this is what we call as the error syndrome. If they are equal to 0, then it means that what you are sending is correct. There's no need for you to do any error corrections. So okay. So obviously we you can see that this is 3 times 6 matrix, and then your y is 6 times 1. So your syndrome is obviously 3 times 1 vector. So that's why your error syndrome lives in n minus k vector space. So here I also mentioned that if your transmitted information is inside your code words, it means that your h multiplied with your vector y equals to 0, and you don't need to you fulfill the parity check, and you don't need to do any of these error corrections. So let's look at the example that we have just now. So you have the parity check matrix, and these are the 8 code words that I wrote just now. So we also know that the minimum distance for this particular code is given by 3, so it's a 633 code, and it can correct one error because of this. So now what does the whole error correction tries to do? So this is what we call as the standard array. So the first one that okay, it doesn't want to go into. So this one is your code words as defined over here. And then this will be the errors that you introduce to it. So this, we call this as a coset leader. I don't want to define what is a coset because it's already very mathematical. But if you want to know, the name is called a coset leader, but it doesn't matter whether or not you understand the name. The point here is that whenever you try to introduce some part of errors into your code words, so you just introduce one error. So you can notice that if you sum these two vectors together, you get 0, 0, 0, 0, 0, 1. So over here, if you want to introduce the error on the very last bit, you change one time. So all of these, I try to introduce the error on the last bit. And then this will be introducing the error at the second last bit. And you can see that only the second last bit changes for everything. So the reason why you list out the standard array is to show that this particular vector, which is called the coset leaders, when you add on to all your code words, it always form a disjoint set. So it won't mix up with other errors, so to say. So this is what we call as a disjoint set. So this is particularly good for error corrections because now we can try to study, let's say this is the code word that we want to send, and then this is the uh, information that we receive. So obviously, when you compare between the two, you can see that one error happens over here. So you can check back your standard arrays. So your code words that you try to send is 110011. So it is over here. Okay. And the message that you get is 110001. So this is the message that you get. And you know for sure that the error that you want to correct is over here. You can check back over here. So this is the correction that you need to do. So once you sum up with your transmitted information with the coset leaders, you get back your code words. So because over here you have only one error, so that's why you can detect the error. and you can also correct the error. So now let's look at a different example. So the code words that I want to send is the same, 110011. So it's still the same. But now the transmitted information is over here. So of course, you sense that something is not right, and you try to add your coset leaders back to it so that you get back the correct info. So when you do that, you find that you correct back to 011110, which is not the same as the one that you want to send, 110011. So in this case, you notice that there are two errors. You can detect the error because obviously you know that something is not right. And how would you know that it is not right? You can go back to your parity check matrix. So if you want to do the calculation, you can use H multiply with Y and find out what is the vector. You find that it is equivalent to your coset leader. And when you try to correct this particular error, you go to 011110, which is the code word for this column. So even though you can detect the error, you cannot correct the error. Because basically for this particular code, the maximum errors that you can correct is 1. So these are some of the very basic mathematics for error corrections. So now if you are given a repetition code, so what is a repetition code? Just now I mentioned it. You basically have a message bit and you repeat 2 times, so that it becomes 3 bits. So what would be the parity check matrix? What would be the generator matrix? And what would be the code words for this particular repetition code? So maybe I give like 5 minutes for you to figure this out. So for the repetition code, just now I mentioned if it is 0 bit, you repeat 2 more times, so it becomes a 3-bit kind of thing. For 1, you repeat 2 times and then you append them together. So obviously these 2 are your code words. So your code words would be 0, 0, 0 and 1, 1, 1. So just now I mentioned that for your generator matrix, you just take the required basis coming from your code words, and because you cannot take the 0 vector, so your generator matrix is just 1, 1, 1. Okay, so recall that your generator matrix is n multiplied with n minus k. Wait, k. Yeah. Your generator matrix is n multiplied with k matrix. And then your h is n minus k multiplied with n. So your generator matrix is 3 times 1, which is correct. So now your parity check matrix has to be 2 times 3. So what would be that? Try to find this. H multiplied with G equals to 0. And you would get H probably will be something like this. So you can check that H multiplied by G is indeed equals to 0. So just to write down everything formally, your 313 code would consist of G equals to this, H equals to this, and then your code words will be 0, 0, 0, 1, 1, 1. So if you were to write down the array, the standard array just now, so your code words is 0, 0, 0, and 1, 1, 1. And then you need to introduce your errors, and your errors, what is that called? The Hamming distance is of distance 1 from your code words. So in this case, it will be 0, 0, 1, 0, 1, 0, 1, 0, 0. Over here, it will be 1, 1, 0, 1, 0, 1, 0, 1, 1. So you see that this particular standard array does fulfill everything coming from the previous example that we studied. So this would be your 313 code. So your 313 code and your 633 code, what are the differences? This is 633. Yeah. So what would be the difference between the two? The similarity is that they both fix one error. And there's no more similarities. The difference is for the first one, you only encode 1 message bit. For the second one, you encode 3 message bit. So if you were to use the repetition code to encode 3 bit of message, if you were to use this particular code to encode 3 bit of message, you will need 9 bits in total. So in that case, your 633 code is an improvement because you only need 6 bits. So I think this is more or less what I want to cover for the classical error correction. So just now I mentioned like your H and your G, basically they are like dual to each other. You can think of it as covariant vectors and contravariant vectors, if you know what that is. But basically, classical error corrections plays around this kind of idea, whereby you try to establish an orthogonal subspace within a bigger subspace. Um, so let's say this is a bigger subspace. You have two orthogonal subspace. One would be your code words. The other one would be your syndrome. So if they are as separated as possible, then it's easier for you to identify more errors. If you somehow have overlaps, then your your codes are not a very good one. So the optimization usually comes from how many message bits that you can encode, and then how many bits in total that you are going to use. I won't go too deep into the classical error corrections, but instead now I want to go into the stabilizer formalism. But before that, we need to know a little bit of group theory. Again, this is quite mathematical. Basically, what is a group? A group is just a set with a binary operation that you try to fulfill 4 conditions. The first one is associativity, meaning you fulfill this equation. Second one is that you have a unique identity. So identity multiply or perform any binary operations on the elements of the group G. It gives you the elements again, the element group G, which is A again in this particular equation. You also have what we call as the inverse, which is denoted by A prime. And lastly, whatever you are trying to perform under these binary operations, it must go back to the group G, which is close under the operations. So when you satisfy all these 4 conditions, they are a group. So now questions. Is the first one a group? I need someone to answer. Or you can type in chat if you want. I suppose nobody types in chat. The first one, the set of all positive integers with operation plus. Is this a group? This is actually not a group because you don't have identity. So it's not a group because you don't have identity. You don't have inverse. Okay. The second one, set of all positive integers. Now the operation is multiplication. Is it a group? It is still not a group. Message. Okay. Yep, it is still not a group because with multiplication you don't have inverse. You have identity, but you don't have inverse. Okay. Third one, non-negative integers, meaning that you include the point 0 with addition as your operations. it is still not a group because you don't have inverse. The fourth one, all integers with operation plus. This is a group. The last one, all positive rational numbers with multiplication. This is also a group because you have identity and then you have inverse. So mostly we are trying to focus on finite groups because later on when you look at the Pauli groups, it is finite groups. Finite group means that you only have a finite set of elements and you can construct your group multiplication table easily. So if let's say you only have two elements, identity and another group element A, so then the only way for you to fill in the group multiplication table is that when identity multiply with identity, you get E. Identity with A, you get A. A with E, you get A. So A, when you put in A again, you have to put E. You cannot put A again because it will break your multiplication. So this is the only way for you to write down the table for a two element finite group. Try to fill in this one. Can this be A? This cannot be A, right? So can this be E? So if let's say you fill this as E, which is your identity element, then this has to be B because each row and each column you cannot uh, repeat your elements. So if you do it this way, you satisfy the row part, you don't satisfy the column part. So this is not the way to fill it. So then this is the only way that you can write down the multiplication table for Z3, a three element finite group. So then this is obviously E and then this is A. So there's only one way for you to write down the group multiplication table with three elements. So as I mentioned just now, when you try to find the multiplication table, you have to preserve the uniqueness of inverse elements and identity. So that's why each row and each column you can only have one of these elements appear once. So because for finite group of two elements and three elements, there's only one way for you to write the group multiplication table. So it means that for any groups with two elements and three elements, that will automatically satisfy this group multiplication table. So this is what we call as the isomorphism, which I don't want to go into and define that again. Um, so now for 4 elements, you will have two different types of multiplication table. The first one is what I call as Z4. The second one is what I call as V. So I will just tell you that for V, these are the identity elements. So maybe I give you like 5 minutes for you to fill in the rest. So if you can fill it in, you should be able to get these two group multiplication table. You find that structurally they are totally different. So you cannot convert between these two. So there are two different group structures. So They are not isomorphic to each other, in other words. Okay. Um, so what will be the example for Z2? You can consider, sorry, Z4. You can consider Z4 as plus. And you should be able to see that it satisfies the Z4 group structure. For V, currently I don't have good examples. But let's move on for now. So let's look at a subgroup. So the definition of subgroup is that H, first thing, has to be a subset of your bigger group. And then you must have the same group operation with the bigger group as well. So this is what we call as the induced group operations. So if you satisfy these two conditions, then H is a subgroup of G. They are what we call as the proper subgroup and improper subgroups. So improper subgroup basically is your identity and the group itself. So other subgroups will be called proper subgroup. So now the first one, is the first one a proper subgroup? The Z with addition, is it a proper subgroup of the real number with addition? So this is a proper subgroup because Z is a subset of R, and then you also inherit the same operations. The second one is not a proper subgroup because the operations are different. So the last one, operations are the same, and then Q is indeed a subgroup of R. So this is a proper subgroup. So the next one, going back to your Z4 and V, write down for Z4 all the proper subgroups, and then V all the proper subgroups. So for Z4, it's quite easy to identify. There's no proper subgroup for Z4. Because when you look at A multiplied with A, you get B, and then you need to include B, and then you need to include C. So in the end, the only subgroup for Z4 is E and the whole group by itself. So now let's look at V. V would have EA because A multiplied with A, you get E, and then you have EB, you have EC. Sorry, for Z4, I think there is one. Let's see again. Yeah, Z4, there is one. Actually, EB. A, you cannot do it because A, you need B, and then from B, you need C as well. B, when B multiply with B together, you get E. So E and B, they form a proper subgroup. C you cannot do it because C multiplied with C you get B, and then you need A again. So for Z4 you have EB. For V you have EA, EB, and EC. Yep. So that will answer this question. So looking from the table just now, the way I do it is quite obvious. You can see, let's fix the identity element and then one of the element first. If A multiplied by A, it goes back to the identity element, then that itself is a subgroup. But in this case, it goes to B, so EA cannot be a subgroup, but EB can because it goes to identity. EC cannot because EC goes to B. So over here, you can see more obviously, A multiplied by A goes to E, B multiplied by B goes to E, same with C. So that's why for the group V, you have 3 subgroups. So these are the conditions for the subgroup. First one, binary operation needs to be closed on H. You need to have your identity, and then you need to have your inverse. So now at this point, let's look at the table that I typed out. So if for Z4, you want the subgroup to contain element C, how big would be the so-called subgroup? So then you start with, sorry, you start with E and C. So E multiplied by C, you get back C, no problem. So now the next thing is C multiplied with C, you get B. So you have to include B. And then B multiplied by B, you get E, so that's fine. But C multiplied by B, you get A. So you need A as well. So basically, if you need to contain the element C, it has to be Z4. Now let's look at V. If you want to contain the elements C and E, basically that's it. Because C multiplied by C, you get E. It doesn't go out of the loop, so to say. So this will be enough for, this will be the subgroup that will contain the element C for the group V. The reason why we do this particular practice or exercise is to see what we call as a cyclic subgroup. So if there is one element inside what we call as the generator set, then this is what we call as a cyclic subgroup. So you keep on multiplying the same element until you get until the group, all the subgroup elements of H can be obtained. So that will be what we call as a cyclic subgroup. The notation will be given by this, or sometimes this particular bracket. Of course, over here we only look at one element, which is element A. So in a more general case, this can be a set. So then this is what we call as the generating set. The group will not be called cyclic subgroup anymore because the name cyclic subgroup specifically means that you only have one generator. So if you have a generating set, the definition remains the same. So what is the smallest subgroup of a bigger group G, which contains all the elements inside your generating sets? So if you have just one element that generates the whole group, then that element by itself is a generator for the whole group. And it is called a cyclic group if you only have one generator. So Z4 is cyclic because 1 and 3 will be the generators. But V is not cyclic because there's no one element that allows you to generate the whole group through definition 11. So now Z plus the set of all integers with addition, is it a cyclic group? The answer is yes, because it's either +1 or -1. So you just keep on adding 1 or keep on minus 1. Eventually, you will generate the whole uh, set of integers. That's why it's a cyclic group. So now let's go to the Pauli group. We all know that the Pauli matrices, you have x, y, and z. For this particular purpose, we put in um, identity as part of the Pauli matrices. So sometimes you will see me using the sigmas. 0 denotes the identity, 1, 2, 3 denotes x, y, and z respectively. So one thing that you need to take note is that the multiplication of between x, y, and z. So there is this I and then there is this minus sign. So you need to be careful about that. So the Pauli group by itself can be formed by, so this is for 1 qubit. This is the whole group. So basically your group operation is matrix multiplication and your generating set will be x, y, and z. Of course, you need to consider, like for instance, how the product of products x, y, z multiply together. So you have the plus minus version whereby your complex number I is being cancelled off, or you have the I version and so on and so forth. So these are all the multiplications um, consist of x, y, and z. So for n qubits, then you need to specify which qubit that your Pauli matrix tries to act on. So in this case, a more compact notation would be you try to write down the plus minus 1 and plus minus I into the phase like this. And then the generating sets will be x, y, z from qubit 1, x, y, z from qubit 2 until x, y, z from qubit n. So that will be your generating sets. And you just consider all the possible combinations of everything. Then you get your Pauli group of n qubits. So one thing that we try to simplify when we write down this particular notation is that we don't write the tensor product structure. We just write, for instance, if you want Pauli X to act on the first qubit, you write X1. Y2 will be the Pauli Y acting on the second qubit. And then Z3 will be the Pauli Z acting on the third qubit. So this is a notation that we will use from now on. So we know that if you learn a little bit of quantum information, you know that the elements of Pauli groups, they are basically your quantum gates, and they act on your n qubit states to produce another n qubit states. So these Pauli elements, they form a group. So you have a group acting on a complex vector inside the Hilbert space, and it gives you another complex vector which is also inside that particular Hilbert space. So this is what I'm trying to say. Um, Later on, you see why I stress this, because this is what we call as a group action. A group action basically means that you have a group acting on a set of objects, whether or not it's a vector, whether or not it's something else, it doesn't matter. But in this case, we are interested only in the group acting on a complex vector space. So obviously, we also know that we can form a subgroup of the Pauli group. And let's suppose S will be the subgroup of your Pauli group for n qubits. You will have a set of n qubit states, which is a vector. So Vs is the vector subspace spanned by the set of all n qubit vectors. So they will always be fixed by all the elements coming from S. So this is what we call as the stabilizers. The Vs will be the vector space that is stabilized by this particular subgroup called the stabilizer subgroup. S will be the stabilizer for this particular space. So it's quite abstract, but if you look at the equation, it's actually simple. So you know that Pauli matrices x, y, and z, they have two eigenvalues, +1 and -1. So let's not focus on the -1 part. Let's look at the +1 part. So x, which is a group element acting on a complex vector coming from your Hilbert space, and it gives you a +1 eigenvalues of this particular vector again. So you can see that x does not change your vector. Before and after, they are the same. So this is what we call as the stabilizers. So in this case, x stabilizes the plus states, y would stabilizes the plus I states, and then z will stabilize the 0 states. So we look at the next part of the equation later. So now try to do these two questions. Maybe I give 5 minutes. The first one, write down the subgroup that is generated by Pauli X, and then the set stabilized by this particular subgroup. The second one is plus minus X, and then find the set as well. So for the first one, your S should be identity and X. So your VS should be just the span of your plastics. The second one, your S should be plus minus identity plus minus X. Your VS will be trivial. Trivial means that you don't really have an answer. The reason why is because of your minus identity. Whatever states that it acts on, it doesn't give you back your sign because of this minus sign, right? So then the only thing that this equation can satisfy is for psi to be 0. That's why it's a trivial vector space. So the third one, find the set Vs such that the whole Pauli group will stabilize us on. So in this case, I will just give you the answer. Your whole Pauli group is like the generators for X, Y, and Z, and each of them stabilizes different elements of your qubit. So X stabilizes plus, and then you have plus I, and then you have 0. None of them are common. So that's why your Vs is still a trivial vector space. So this question is interesting. Try to do it. So you have two generators, Z1, Z2, and Z2, Z3, meaning that this is coming from the Pauli group of 3 qubits. So for this particular subgroup, you have identity Z1, Z2, Z2, Z3, and then you try to multiply between Z1, Z2, and Z2, Z3. It will give you Z1, Z3. I think that's all. So this will be the set of all elements inside this subgroup. So now let's look at the elements of this stabilizer subgroup one by one. We don't need to look at identity because plus identity will stabilize everything. So let's look at Z1, Z2. If it acts on a 3 qubit states, what kind of what kind of basis will give you back the same states? So just think of this particular equation and think of 3 qubit states with 8 bases. So what kind of basis will satisfy this particular equation? So the first one obviously is 0, 0, 0. And then you have 0, 0, 1. And then you have 1, 1, 0 and 1, 1, 1. So the reason why 1, 1, 0 satisfy this particular equation is because for the first qubit, you have a minus sign coming out because of this. And then the second qubit, you also have a minus sign coming out. So the minus sign cancel off. That's why you have 1, 1, 0 and 1, 1, 1. So that's Z1, Z2. So now let's look at Z2, Z3. So applying similar logic, you will have 0, 0, 0, 1, 0, 0, and then 0, 1, 1, and 1, 1, 1. Z1, Z3, you will have 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1. So besides your identity matrix, you basically identify the bases that will be stabilized by the 3 elements inside your stabilizer subgroup. So the rest is to look at the common basis, which is the 0, 0, 0 and 1, 1, 1. So it means that whatever vector space that is spanned by this um, basis, basically that will be stabilized by this particular stabilizer subgroup. So your VS would be the span of the 0, 0, 0 states and the 1, 1, 1 basis. So that would be the answer for this particular question. So from all these 4 questions, you can conclude the following. If you want to check whether or not a particular vector or a particular basis can be stabilized by the whole group, you actually don't need to check for the whole group. You just need to check for the generators. So for the sake of demonstration, I show everything, but you can simply just check Z1, Z2, and Z2, Z3, and you will get the same conclusion. The 0, 0, 0 and the 1, 1, 1 bases, they are being stabilized by the whole group. The second one is that if you don't want a trivial vector space, all the elements inside your stabilizer subgroup has to be commutative, and then minus identity cannot be the element of your stabilizer subgroup. So the minus identity part I already described over here. If you have a minus identity, you cannot satisfy this equation unless your vector is equal to 0. That means that it becomes a trivial vector space. As for the commutative part, look at the first question. So you have x, y, and z. So you know that x, y, they are not commute to each other. So that automatically sort of like tells you that the second condition has to be true, this part. So how does this being used in error corrections? Oh, before I go to here. So over here, I show one sort of like example of the duality that I mentioned just now. So if you look at the classical error corrections, basically they use the duality between your linear dependence of your um, subspaces between the vectors and the dual of the vectors to do error corrections. So what this particular stabilizer formalism tries to tell you is that um, you can either describe the stabilizer or you can either describe the geometry. So in this case, if you have a equilateral triangle, so that's you trying to describe the geometry of stuff, but you can also ignore the geometry part and just look at the stabilizers. So if you just look at the stabilizers, then you are basically talking about rotations of 120 degrees. And as long as your shape satisfies the symmetry coming from this particular rotation group, then you are getting stabilized by this particular cyclic loop. So that's why your stabilizer group sort of like provides an alternative description without having you to refer to the geometry part. As for the error correction part, what we are going to make use of is actually the second half of these equations, because so far whatever we are trying to do, we want the positive one eigenvalues. So it means that whenever you get a minus eigenvalues, something else happens, and that something else is what we call as the Pauli errors. So let's look at a very simple case, 3-qubit bit flip code. So this is the quantum circuit for the bit flip code. This part is you trying to entangle the first 3 qubits. So this will be the 3 qubits that you want to uh, sort of like preserve using the quantum error correction codes. And then you have these two as your parity check. So over here you have errors. So the error that I try to introduce in this case is your Pauli X. So notice that after I introduce the error, I have to do a parity check between the first 2 qubit and then the first and the third qubit. So this is entanglement. You try to how should I put it? You try to entangle the first 2 qubits to over here so that you can perform measurement and then do the parity check. Similarly over here as well. So so let's look at the first one where there is no bit flip error happens. Notice that the measurement that I try to compare over here is Z1, Z2, and Z2, Z3. And this is exactly your stabilizer for these bit flip codes, for 3-qubit bit flip codes. So for the quantum version of your linear codes, you use double square bracket. So in this case, this is a 3-qubit encoding 1 qubit, and then you can fix one error. It should be 311 if not mistaken. So let's study this particular table one by one. So you don't necessarily need to perform this one, because having this one, these two parity check will be enough for you to detect the errors. So if there's no error coming out from your parity checks, you should observe +1 eigenvalues when you do the measurements. But as long as you get the Pauli X on your first qubit, so whatever measurements that you try to perform that involves the first qubit, you will gain a minus sign. So that's when you know that something is wrong with your first qubit, because your first qubit Z1, Z2 get a minus sign, but Z2, Z3 is positive. That means that your Z2, Z3 has nothing happen. Similarly over here, Z2 both are negative because both parity checks involve the second qubit, and so on. The last one, it will be the Z2, Z3 that involves the third qubit. That's why you get a minus sign. So the minus sign signifies something is wrong with your quantum states, and you need to fix it by looking at this particular table. So now we know that for a bit flip code, your generator is Z1, Z2, Z2, Z3. So what would be your VS? Just now we already studied. It will be the span of 0, 0, 0 and 1, 1, 1. Okay. So now if you have a phase flip code, so same thing, you do the entanglement. These two are the parity check bits. These two are the repetition qubits. Now I do so this whole thing is what I call as the phase error. Ignore why there is a Hadamard gates over here first. Uh, that won't be covered in this particular uh, discussion. So for now, just think of this whole block as a phase flip error. So similar thing, you try to compare after that the parity of it. So now what is the generating set of the stabilizer and the set of VS? So we know that the phase error is coming from your Z gates. Okay. So your generating set has to be the X. Because X will not be commuting with Z. So then later on when you uh, build this particular table, you will then notice the -1 parity whenever there is a Z error happening. Okay, so Z would be sorry, for the phase flip code, your generating set will be x1, x2, x2, x3. You can also write x1, x3, x2, x3. It doesn't matter. So you just need two elements. Your VS will be the span of the plus 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 and the minus minus minus. So that will be your phase flip codes. So roughly speaking, this is how a linear code for quantum error correction works. Of course, this is just the beginning. You have something more complicated going on later on. So this is just a very introductory level. The last part is actually what I want Jianhao to do. So I introduced what I call as the cluster states. They are just very special graph states, which are used in measurement-based quantum computing. At this point, you don't need to know what is that. You just need to know that this is graph states and how to construct your cluster states. So you look at your graphs and then you begin with ground states on all qubits. You apply Hadamard gates on all qubits and then control Z on qubits that are connected together. So let's look at the first one. You have two qubits and this is a graph state. It shows you the qubit 1 is connected to qubit 2. So you begin with 0, 0 and then Hadamard on all qubits. So it becomes plus. And then control Z on the qubits that are connected together. So it means that let's say this is the qubits. So because qubit 1 is connected to qubit 2, so you need to do C naught. So then what you need to do is you basically need to expand everything. So you write down 1 over 2 because this 1 over square root 2 multiplied together to get 1 over 2. And then you have, let me write down the states at this particular point. It will be uh, 0 plus 1 tensor with 0 plus 1. So this is a state at this point, if I write it correctly. Then after the C naught, so you have to, okay, let's do this. So after the C naught, what you would get is 0, 0, 0, 1, 1, 1, 1, 0. Did I do this correctly? Apply C naught. Wait. Ground states, apply Hadamard's. C naught, they are connected together. I might be missing one step. I need to check back the steps. I think I missed something over here. The answer should not be this. Yeah, the answer should not be this. I think I missed one step over here. So let me get back to you later. What did I miss over here? But essentially what I want Jianhao to do is start constructing this, the cluster states for the first one and the second one. And then the reason why I study cluster states is because it is also a form of stabilizer states, whereby you can write down the generating sets of stabilizers very easily by this equation. So this is to Jianhao, by the way. This is the way for you to write down the pure states through these steps. I think I missed one steps over here. Let me check again. This is the way for you to write down the generating sets of stabilizers. So for 2 qubits, for example, is quite simple. So your Ni will be the neighboring index. So what does it mean is that you have 1 qubit over here connected to another qubit. So when you focus on the first qubit, your Z will be coming from your neighboring index. So you have Z1. And then because you are connected to the second qubit, so you have X2. And then now you focus on the second qubit, so you have Z2 and then X1. So that is how you formulate the generators of or the stabilizer for your cluster states. For the first qubit, you can do it for the second one. it should not be that difficult. It should be just Z1, X2, uh, X1, Z2, X3, and then X2, Z3. So that will be your stabilizers for um, this setup. I already do it for you. Try to verify for all the cluster states in the paper. And then finally, the very good thing coming from the cluster states above is that you can also write down the density matrix very easily. So because you already know the generators, so what you need to do is to write down this particular product. Sorry, it's a product, it's not a plus. So it's not a plus, it's a product. So same thing over here, it's a product. So then over here, for example, the first example, the 2-qubit one, it will be just 1/2 identity plus Z1 X2, and then you have another 1/2, that's why you get 1/4. So that will be your density matrix for the first one. And then the second one, you just do this particular equation accordingly, and you should be able to get all the cluster states that I have in the paper. So try to replicate everything. If you want to make yourself believe that this is true, let me double check again the steps over here. What did I miss? Then I get back to you. Um, yeah, particularly you need to convince yourself that from the pure states coming from these two things, you can formulate the density matrix, and they are the same as what you do for equation 26. So that will be your assignment this week. I think I will just stop here for now.